So in previous chapters, we talked about how to use the mean and standard deviation to describe the distribution. In this chapter, we're going to talk about how to transform each score into standardized scores so that we can see the exact location of each score within a distribution. So with a score on its own, say you got a 76 on a test, it doesn't mean much unless you know about what the rest of the class looks like or what the rest of the scores look like. So if the class average was a 60 and you got a 76, you did pretty well. If it was a 90, you didn't. Those comparisons to other scores is really important. Okay, so we're talking about z-scores today. And the primary purpose of the z-score is to describe the exact location of a score within a distribution. And so a z-distribution has a mean of 0 and a standard deviation of 1. So a z-score basically transforms each x value into a number with a sign, positive or negative. And the sign tells you whether that score is above or below the mean. The number tells you the distance between the score and the mean in terms of the standard deviation. So the locations identified by the z-score are the same for all distributions. We'll see a little bit more what that means in a minute. But again, with the z-score, the absolute value of a number of the z-score is the size of the number, regardless of the sign. So this is sometimes, absolute value is sometimes notated using these lines. And so the absolute value of +2 is 2, and the absolute value of -2 is 2. So it's just without the sign. So the symbol plus or minus, this symbol means plus or minus, therefore plus or minus means 1, 1 means positive or negative 1. Okay, so this is an example that we will use, and we can see that this is a normal distribution. Okay, this has a mean of 60 and a standard deviation of 5. So this is a frequency distribution for attractiveness scores. So when we talk about z-scores, like any raw score, a z-score is located on the distribution. So z-scores can be individual scores, and a z-score is also automatically communicates the raw score's distance from the mean. So if you're looking at a score that has been converted to a z-score, you know a lot of information about that score. You know how far the score was from the mean and whether it was above or below the mean in terms of the number of standard deviations. So the z-distribution represents the proportions of population data, so the proportion of scores in a normal distribution that fall within a given number of standard deviations from the mean. Okay, so these are always the same because we're standardizing to z. So we always know that 34% of scores fall between the mean and 1 standard deviation. 34% fall between the mean and 1 standard deviation above the mean, and 34% are between the mean and 1 standard deviation below the mean, which means that if we add those two together, 68% of scores fall within plus or minus 1 standard deviation of the mean. That means 68% are either 1 standard deviation above or below, between 1 standard deviation above and below. For 2 standard deviations, we know that 95% of individuals or scores will fall within plus or minus 2 standard deviations of the mean. So the general guidance is that 68% of scores are plus or minus 1 standard deviation, 95% are within plus or minus 2, and 99% are within plus or minus 3. Okay, so the vast, vast majority of scores are within 3 standard deviations of the mean. Okay, so a z-distribution is a distribution produced by transforming all the raw scores into z-scores. Okay, so you can transform every single raw score into a z-score, and when you plot them, you get a z-distribution. And a z-distribution may be used to determine a raw score's proportionate rank in a set of scores. And this is the formula for computing a z-score for a raw score from a raw score. Okay, so the z equals x minus mu divided by the standard deviation. We are looking at how the deviation from the mean compares to the standard deviation. So we have this standardized distance from the mean. So if we know the z-score and the mean and the standard deviation, we can also figure out what the raw score is, right? So when a z-score and the associated mean and standard deviation are known, then we can use those to compute the raw score. So the formula for this would be x, because we're trying to get the raw score, equals the z-score times the standard deviation plus the mean. Okay, so we can rearrange this formula to compute any of the components, right? So if we know all of the information except for the standard deviation, we can solve for the standard deviation. If we know all of the information except for the mean, we can solve for the mean. So we'll be doing lots of problems that kind of are variations of the same formula. Okay, so this is basically what a Z transformation looks like or does. It does not change the shape of the data. So let's say we had IQ scores or something like that. We have this sample or this population, because I'm using mu. So we have this population where we have a mean of 100 and a standard deviation of 10. Okay, we can convert all of those X scores, because those X scores are in the original unit. We can convert them into Z scores, and our Z distribution always has a mean of 0 and a standard deviation of 1. So 10 points on the X score in this case corresponds to 1 point on the Z score. Right, so the distance on the X score, 1 standard deviation, is equivalent to 1 point on the Z score. In addition to knowing the basic definition of the Z score and the formula, we can also visualize Z scores as location on the distribution. Okay, so the fact that the Z score identifies the exact location within a distribution means that we can use Z scores as kind of a descriptive statistic as well as inferential statistics. So as descriptive statistics, Z-scores describe exactly where an individual is located. So we remember that the Z equals 0 at the center, at the mean, and the extreme tails correspond to Z-scores of -2 or +2, right? So if we know an individual's Z-scores, we can visualize where they are on the distribution. And again, it's possible to have Z-scores beyond negative or +2, but it's extremely unlikely. When we get to inferential statistics, we'll talk about how Z-scores might be used to determine whether a specific sample is representative of its population, or if it's so extreme that it might be unrepresentative. Okay, so when an entire distribution of X values is transformed into Z-scores, the resulting distribution of Z-scores will always have a mean of 0 and a standard deviation of 1. So if we convert every single X into its corresponding Z-score, we create a new distribution. I'll show you what that looks like in just a second. But when we do this, it's important to note that the transformation does not change the shape of the original distribution. It doesn't change the location of any individual score compared to others. But what converting a distribution into Z-scores does is it changes the mean to 0 and the standard deviation to 1. Z-scores always have a mean of 0 and a standard deviation of 1. Okay, so let's say we had these raw scores and we can see our data is kind of messy. It's not a perfect normal distribution, but in this data, we've got a mean of 3 and a standard deviation of 2. If we convert every single score to a Z-score, we end up with a distribution that looks exactly the same, but it has a mean of 0 and a standard deviation of 1. This individual who scored a 0 here now has a z-score of a minus 1.5. This individual scored a 6 here, has a z-score of positive 1.5. So it's definitely not a normal distribution, but you can see it looks the same whether it's in the metric of x or z. So the advantage of standardizing your distributions is that we can compare distributions from different numbers. We can compare two different distributions and make them the same. So for example, if we have maybe scores on two different tests, and one of those tests has a mean of 100 and a standard deviation of 10, and another distribution has a mean of 40 and a standard deviation of 6, it's hard to compare those because we don't know, we can't directly compare them. But if we convert every score to a z-score, then both of our distributions will have a mean of 1 and a mean of 0 and a standard deviation of 1. Okay, so we can see this something like this, where we have individual scores on statistics and their scores on English. These are their specific scores. So the statistics scores range from 15 to 45. The English scores range from 10 to 70, but we can convert both scores into z-scores, and so we can lay them on top of each other. So because the z distributions all have the same mean and same standard deviation, the individual scores can be directly compared. So if we want to know if you get a 40 on your statistics exam and a 50 on your English exam, it might be tempting to conclude that you did better in English. But if you look at the z-scores, a z-score of 40 in stats is actually a score of 40 in stats is actually a z-score of +2. So you are on the very high end of this distribution for stats, whereas a score of 50 for English is only a z-score of +1. So in comparison, you actually did better on the statistics test than you did in English when we take into account how the rest of the class worked. So although transforming x values into z-scores creates a standardized distribution, sometimes people find z-scores kind of burdensome because they consist of many decimal values and negative numbers. Therefore, it's more often convenient to standardize the distribution into numerical values that are simpler than z-scores. So to create a simpler standard distribution, you might select the mean and standard deviation that you would like to see for the new distribution. And then we can actually take z-scores and convert them into a different distribution. So if you were to do this, you'd select the mean and standard deviation that you want for your new distribution. So say, you were looking at IQ tests that had a mean of 57 and a standard deviation of 8. Those are going to be hard to remember, but you want to convert them to a distribution that has a mean of 100 and a standard deviation of 10. We can use that z formula to convert each individual score into a z-score and then transform those z-scores into the distribution that you want. Okay, so often this is used for things like the SAT or intelligence tests. This is basically the example that I gave you. So we have an example where you want to standardize distribution so that the new mean is 50 and the standard deviation is 10. So we have an individual with a z-score of -1 in the original distribution. We would assign them to a score of x equals 40 because this score is below, a z of -1 tells us it's below the mean by 1 standard deviation. Our mean is 50. We subtract 1 standard deviation. That gives us our new x score. So if you repeated this process for each individual score, it would allow you to transform an entire distribution into this new standardized distribution. Okay. So a final note is to remember that we've been dealing with mu and sigma. So we've been talking about so far population scores. It's possible to calculate z-scores from samples as well. And the biggest thing to really remember is that the big change you have is how you compute the standard deviation, where with a sample, we're dividing by n minus 1 instead of n when we get the variance. But the definition of a z-score is the same for either a sample or a population. The formulas are the same, except that the sample mean and the standard deviation are used in place of the population mean and standard deviation. Okay, so if you use a z-score to standardize the sample, it has the same effect as standardizing a population. The shape's going to be the same as the original shape. The mean of the z-scores will be 0. The standard deviations of the z-scores will be equal to 1, assuming that you calculated your standard deviation correctly. Okay, so a couple of the key points is that a z distribution always has the same shape as the raw score. The mean of any z distribution is always 0, and the standard deviation of any z distribution is always equals 1. And what z really does is establishes a relationship between the individual score, the mean, and the standard deviation. And so we'll go over examples of how to calculate this in class.